Okay, so we have seen how the residue theorem allows us to compute contour integrals of apparently difficult looking functions, difficult looking contour integrals fairly simply by just computing residues at certain strategic points, right? So whenever if we have information about all the isolated singularities, then we basically are able to compute complicated looking contour integrals with ease. So in this lecture, we will see how we can exploit this to obtain some interesting results for integrals involving just real variables. Okay, so before we uh, get into how to go about this, first there's a useful notion which uh, it's worth making precise, right? So oftentimes we are interested in working out integrals, where the limits of integration go from minus infinity to plus infinity. So what we want to do is be able to come up with a contour, along the x-axis, where it actually comes all the way from minus infinity, goes all the way up to plus infinity, but not quite, right? We have to come up with a limiting procedure. So we will consider a curve like this and say, if by some means we can argue that we have some integral like f of x dx, then we elevate this f of x to f of z and make it a function of a complex variable, and then perform a contour integral around this. And if by some means we're able to argue that in the limit of this radius r becoming very large, right? So in the limit of r tending to infinity, if we can somehow argue that the contribution which is coming from here is 0, and then basically we will get the value of this integral along this x-axis for free if we are able to work out the contour integral, which in turn can be done by just finding out all the poles, right? If there is a bunch of singularities sitting at these points, we just need to evaluate the residues at these points, and then we have the answer, right? So that's basically the philosophy of this method. But before we do that, it's important to discuss the idea of the Cauchy principal value, right? So when we have an integral like this, some f of x dx from 0 going from 0 to infinity, what we mean is we do the integral from 0 to r f of x dx and then take the limit r going to infinity, right? If we have both the limits plus and minus to be infinite, then what we mean by doing this integral minus infinity to plus infinity f of x dx is, separately you break it down from minus infinity to 0 and then from 0 to infinity, and then ascribe this meaning to it. Limit r1 tending to infinity and r2 tending to infinity separately. The first integral is from minus r1 to 0 and the second one is from 0 to r2, right? So this is what is meant by this integral. But often it's also useful to think of another quantity which is very closely connected, and that's called the principal value of such an integral. So that's called the Cauchy principal value, and what the way to define this is, just put one r. So you box this function f of x between minus r to plus r and take the limit r going to infinity. There's just one of these, one limit is taken, right? So I mean, it might look like really both are the same, and often they are, right? But there are cases where these two quantities are not quite the same, right? So if this integral exists, if both of these limit exists, then for sure it's the same as the Cauchy principal value. But the other way around may not be true. So let's look at an example, right? So the standard example is to consider something like just x dx, and you go from minus infinity to plus infinity. So the principal value is simply, r tends to infinity minus r to plus r x dx, and but this is x squared by 2 minus r to plus r, and r tends to infinity, but r squared minus r squared is basically 0. So doesn't matter how large r is, this quantity is 0, the principal value is 0. But on the other hand, if you were to evaluate the other limit minus infinity to plus infinity as minus r1 to 0 and r0 to r2 separately, and take these limits r1 and r2 to go to infinity, then you get a different answer. You see x squared by 2, 0 and minus r1, and limit x squared by 2 from 0 to r2, right? So you have a scenario which is, it's like minus infinity and plus infinity, right? So which is well, I mean, it's so it's 0 minus r1 squared. So it's going to be minus infinity. So you cannot add these two, and there's no well-defined answer for this. So it's actually indeterminate, right? So these two limits don't separately exist, and so you say that this is not defined, right? But the Cauchy principal value of this integral is defined, right? There is one special case where for sure this integral is the same as the Cauchy integral principal value, and that's when f of x is even, right? So the way to see that is, if f of x is even, I mean, we can write minus infinity to plus infinity f of x dx as this according to the definition, and then because f of x is even, so we can write integral minus r1 to 0 f of x dx is the same as half of minus r1 to plus r1 f of x dx, and again r2 0 to r2 is the same as going from minus r2 to plus r2 and then dividing by 2. Now, but each of these is separately, this is half times the principal value, and this is again half times the principal value. In place of r1 and r2 here, we can just call it r, and then we immediately see that this is basically the principal value. So half the principal value plus half the principal value is the principal value. So you get principal value of minus infinity to plus infinity f of x dx. Right. So the reason why we want to clarify this is because when we are coming up with contour integrals, often it is really the principal value that we are working with, right? So we want to take, define something like this, come up with a contour, and then take the limit r going to infinity, right? So that's the reason why we want to make this notion clear. Now, I said the other ingredient in being able to evaluate in such integrals along the x-axis is to be able to convince ourselves that the integral along this this large semicircular region, that must go to 0, right? So that's where this thing called the Jordan's lemma comes into play. So I'm going to try and motivate a somewhat more complicated example where the Jordan's lemma is important, but there are scenarios where even without the Jordan's lemma you can directly sort of argue that because r is becoming very large, the contribution along this semicircular part is going to go to 0, right? So there is a way to argue for that, but let's look at what is called the Jordan's lemma, right? Often we are interested in integrals of this kind, right? So we are interested in integrals of this kind, f of z times e to the iaz, right? So this comes about when we are working with Fourier transforms, for example, right? So we are interested in f of x times e to the iax, right? And in that context, we do encounter, integrands of this kind, f of z times iaz. So now, if this function obeys certain conditions, which we will state immediately, then we can argue that the value of this integral along this semicircular arc is going to be 0, right? So first of all we consider this function to be analytic at all points in the upper half plane that are exterior to some circle. So what it means is all the isolated singularities, all the poles which occur in the upper half plane are located in some finite region, right? Beyond that, you'll always be able to come up with some sufficiently large circle or semicircle beyond which there are no singularities. It's completely analytic, right? So that's the type of scenario we're looking at. And then we consider a semicircular contour CR whose radius r is greater than this r0, right? So r, that means that our contour basically for sure includes all the poles, all the isolated singularities of this function f of z are contained inside this, and then our function, our CR, the function on CR is bounded by a radially sufficiently rapidly decaying positive constant. So what it means is mod of f of z is less than or equal to mr. Right now, this bound is going to depend on r, but that bound is such that it becomes smaller and smaller as r becomes larger and larger. And in the limit of r going to infinity, mr is actually 0. Right? So basically, this function is, is not some weird function which will blow up at infinity or something. It's going to keep on decaying. Basically, that's what it means. And if that holds, then what Jordan's lemma says is, this, then you can basically ignore the contribution coming from this semicircular large arc, right? So let's see how this Jordan's lemma comes about. It ultimately connects to something called the Jordan's inequality, right? So that's just a simple integral. So suppose you consider this integral 0 to pi e to the minus r sine theta d theta. You can write it as 0 to pi by 2 and then pi by 2 to pi, the same integrand, and then you can do a shift in theta. So instead of writing it as just, so you introduce this change of variable for the second of these integrals. So in place of theta you call it pi minus alpha, and then the limits will be pi by 2 to 0, and you might as well call it pi minus theta. So in place of d theta minus d theta, and then you see that sine of pi minus theta is the same as sine theta, and this minus sign goes here, and basically you get that this integral is the same as this. So in fact this integral on the left hand side is 2 times this integral from 0 to pi by 2, same quantity, e to the minus r sine theta d theta. Now you argue that in this region 0 to pi by 2, sine theta is always greater than or equal to theta by pi, right? So basically one way to think about this is, theta is 0 at 0, and 2 theta pi is also 0 at 0, and 2 theta pi is 1 at pi by 2, and sine theta is also 1 at pi by 2. So basically this curve 2 theta by pi is like a straight line that you join between 0 and the point maximum point of the sine curve at pi by 2. Now sine is always going to be above this straight line between these 2 points, as you can check by just plotting it, for example. So therefore, since sine theta is greater than or equal to theta pi in this entire regime, so this integral is going to be less than or equal to 2 times 0 to pi by 2 e to the minus r 2 theta by pi d theta. But this integral is something you can work out explicitly, and we immediately have the result that this is this integral is equal to pi by r times 1 minus e to the minus r. So basically we managed to immediately show that this is the Jordan's inequality. We have managed to show that whenever r is positive, which is the case here, it's a radius and so it has a positive value, 0 to pi e to the minus r sine theta d theta is less than pi by r, right? So that's the Jordan's inequality, and our Jordan's lemma actually follows from this. So what you do is you write down this contour integral IR over CR. CR is this big semicircle, f of z e to the I a z dz, and then you write it as 0 to pi d theta, so Ri e to the I theta d theta in place of dz, and then we have in place of e to the I a z, you write it as e to the I a r e to the I theta, and f of r e to the I theta also you have here. So but mod of f is given that this function f of z is going to be less than or equal to mr on this semicircular region. So f of z is decaying as you make r and r larger and larger, its magnitude is falling, and on the other hand magnitude of this quantity is basically just given. So you have in place of e to the I theta, you can write it as cos theta plus I sin theta. Cos theta will only contribute to the phase, plus I sin theta will become e to the minus ar sin theta. Right? So basically what we have is, if I take the modulus of this integral is, it gives a modulus of this guy or modulus of this, then we basically argue that modulus of this integral must be less than or equal to, pulling out the moduli of the integrand outside, right? So this is like somewhat like the triangular inequality generalized to integrals. So you can pull out this mr times r also comes out, and then anyway, so this quantity is minus e to the minus ar sin theta d theta, and this is something, so we have already seen that's the Jordan inequality will just give us pi by ar, and r will cancel with this, so we are left with mr times pi by a, right? So now comes the key argument from the other requirement. Mr is something which falls off with r, right? So it's not enough that there is an r coming from this integral because it cancels with this r, but we have chosen our mr such that it's going to fall off with r. Therefore mod of ir in the limit r going to infinity is actually 0. Therefore basically ir itself is 0. So we can argue that the contribution from this big semicircular arc is going to go to 0 whenever this condition holds, and often this condition does exist for many useful integrals. So let's look at an example of how this plays out. So we look at an example where the Jordan's lemma plays out. It's essential to to make the argument complete. But there are other examples where a similar trick will hold, and it's easier to argue for the vanishing value of this contour integral along this semicircular path even without invoking Jordan's lemma. So we wish to compute this integral, let's say cos x by x squared plus 1 dx minus infinity to plus infinity. This is not an even function, right? But then it falls off at larger. It's not like f of x equal to x. It falls off on both sides. So basically, it is actually equal to the principal value, right? So in fact, integral minus infinity to infinity cos x by x squared plus 1 is the same as limit r tending to infinity minus r to r cos x by x squared plus 1. But here in this case, it's useful to think of this as the real part of e to the ix. Cos x is the same as real part of e to the ix, and then you pull out the real part, and then you do this limiting operation r tends to infinity minus r to plus r e to the ix divided by x squared plus 1. Then the function that we must consider, the function of a complex variable that we must consider, is e to the iz divided by z squared plus 1. So we wish to evaluate this contour integral, e to the iz divided by z squared plus 1 dz. And what is the contour? The contour is this big, line segment along the x-axis, followed by the semicircular arc, and then you turn around complete the loop, right? So, and then we of course want to imagine taking the limit r going to infinity in this case. Now we have, what is the contour integral along this entire path is actually nothing but minus r to plus r. So that's the integral that we care about, right? So that we can take the real part of this. So this is the part which we care about, plus 0 to pi, this whole stuff, r I e to the I theta d theta. But then we see that mod of z squared plus 1, mod of z squared plus 1, so that's what is in the denominator. Mod of z in the denominator here, mod of z squared plus 1 is greater than mod of z squared minus 1. So that's the triangular inequality, right? So we're getting a, where we have put a greater than symbol here. But mod of z squared is the same as r squared on the semicircular region. So therefore we have this result that 1 over mod of z squared plus 1 is going to be less than 1 over r squared minus 1. So basically we want to argue that this function, just 1 over z squared plus 1, is falling off rapidly enough so that the condition which is given in Jordan's lemma holds. And indeed this is falling off rapidly. As r becomes large, this integrand is going to become smaller and smaller, right? So we just treat e to the iz as separate, and so we immediately see that this contour integral, the contribution from this semicircular arc, this big semicircular arc, is actually 0, because Jordan's lemma holds. We invoke Jordan's lemma, and then we have the result that this contour integral over this entire closed region is actually nothing but equal to the integral that we are interested in. So all we have to do is work out this contour integral. But we know how to work out this contour integral because we can use the residue theorem. So the residue theorem tells us to find all the poles. There are 2 poles for this function. One of them is at plus I and the other is at minus I. And the one at minus I is not within your region of interest. It's only plus I that counts. So by the way, this same kind of a calculation could have been done by completing the loop in the other direction as well. So there are certain problems where it's more useful to go in the other direction. So as far as this problem is concerned, it doesn't matter which direction you go. Jordan's lemma would hold even in the other direction. So as well, provided you can argue for the some conditions which are very similar, but with the direction being different. So here the residue is simple because all we have to do is multiply by z minus I, right? We're considering the pole at z equal to I, so multiply by z minus I and put the value z equal to I. So we immediately get this to be, denominator will become z plus I. So when you put z equal to I, it becomes 2I. Numerator is e to the minus 1. Residue is is there. So the value of the integral very simply is just 2 pi I times e inverse divided by 2i, which works out to just pi by e. Very straightforward. So what we have managed to show is this complicated looking integral minus infinity to plus infinity cos of x divided by x squared plus 1 is actually we have managed to show like the Fourier transform in some sense of this function 1 over x squared plus 1 is well, I mean, you have to be careful because your Fourier transform also involves some k or some other coefficient, right, which can also be written down. But in this case, the specific integral which we started with is this integral, which is obtained as the real part of this quantity which we already worked out, and that is just real part of pi by e is just pi by e. So final answer is very straightforward. And in fact, the technique involved is also very straightforward. It's just that we had to make use of these results along the way, Jordan's lemma, and also one has to be careful because one is considering the idea of a principal value, Cauchy principal value. Once we have this, actually the machinery allows us to calculate these quantities with great ease once we have all the tools. Right? So that's all for this lecture. We looked at how we can apply the residue theorem, how certain complicated looking integrals of real variables can also be worked out. Thank you.